Excellent.
Okay, well, welcome everybody to the Physics Colloquium this week. Today's speaker is Jack Burns. Jack is a professor in APS and has been for about 20 years. Recently, he joined our faculty in Physics 2, and today's colloquium aims to introduce aspect of Jack's research to the department. Apropos to this introduction, I'd like to say a few words about Jack's history, but my words aren't going to be comprehensive, but it'll give you a feeling for the department of feeling of Jack's background. Jack graduated from Indiana University with a PhD in astronomy. He also has a master's degree in higher ed leadership from Harvard. He's academically quite well traveled before making Boulder his home 20 years ago. Before coming to CU, Jack was a professor at the University of New Mexico, where he was director of the Institute for Astrophysics, New Mexico State, where he was department head and associate dean, and also the University of Missouri, where he was also vice provost of research. While at CU, in addition to being a professor in APS and now in physics, Jack was vice president for academic affairs and research for the CU system, where he's now emeritus. Now Jack is director of the NASA-funded Network for Exploration in Space and PI of the Dark Ages Polarimeter Pathfinder, which is planned to go in orbit around the moon in the future. Those are the only words I'm going to say of introduction to Jack. Jack's got a much longer and very textured and interesting history. Jack did ask if there are burning questions about his talk today. Please, you can raise your hand, your little blue hand, but these should be questions about clarification, please. I will look for the blue hands and call on folks. But there should be time at the end for people's questions, given Jack's schedule of the talk today. So Jack, we'll turn this over to you. Welcome to the physics department.
Well, good morning, Mike, and thank you for this invitation to present the colloquium this morning. I'm excited to share the work that my group has been doing on radio astrophysics from the moon. Work that really I've been involved in for over 30 years. In fact, some have referred to me as the chief evangelist for radio astrophysics from the moon, particularly the FARSIDE, since I've been at this for such a long time. Fortunately, we're going to see the first NASA-funded radio telescope on the surface of the moon later this year, and I'll be talking about that. That's one of the four teams that are listed here, and I want to acknowledge that we've got a large number of folks who are involved in these various projects, and I'll be talking a little bit about each one of these. But I also want to introduce members of our research group here at CU, including David Rapetti, who's now actually a senior scientist at the NASA Ames Research Center, spent a number of years here at CU, still a vital member of our team. Keith Taucher, who received his PhD in the physics department here this last summer and is now a postdoc. He's doing much of the same work, only getting paid a lot better. And Neil Bassett and Joshua Hibbard, who are APS graduate students. Also want to acknowledge our funding from the Survey Institute. That's a NASA-funded solar system exploration research virtual institute, and our NEST team that's made up of about 10 universities and NASA centers. Tobin and Mihai have another one of these Survey centers that you all are well familiar with, having to do with dust and dust acceleration. So let's talk a little bit about the history of radio telescopes on the moon. This is not a new idea. In fact, folks had been talking about this and even some discussion at conferences before the Apollo 11 lander. And I wanted to just play you a snippet of an interview by Arthur C. Clarke in 1963 on British television, where he was talking about low frequency astronomy from the moon. Clarke, of course, is famous as the screenwriter for 2001, A Space Odyssey, and just many, many classic science fiction novels. So let me start this, and then I'm going to advance it just a bit to the right spot where he talks about radio astronomy on the moon. So just let me get to this. Yeah, let me start about here.
From electronic devices of all kinds. Moreover, he cannot build the really giant radio telescopes he would like to have because Earth's gravity makes it an engineering impossibility. But on the moon, and particularly on the far side of the moon, shielded from the electronic racket of the Earth by 2,000 miles of rock, there is an ideal site for radio astronomy telescopes. And I think that in a few generations, almost all serious astronomy will be conducted either on the moon or in space.
Well, let's turn now, shall we, to yet another of the pioneer.
Well, so it's now been a couple generations. And we're, as I said, we're finally ready to actually see the radio astronomy from the moon begin. So one of the questions is, you know, why has it taken so long for us to really get there? And I would argue there's really two reasons. One is a science reason. And very simply, up until this last decade, there has not been what you might call a killer science app. That is an application that requires the moon some compelling astrophysics, like what would be recommended by the National Academy decadal surveys, that uniquely requires low frequency observations from the lunar far side. Over the last decade, two very powerful science cases have advanced that do in fact require low radio frequency observations from the moon. One is the so-called dark ages. This is the early universe, before and then going into the cosmic dawn when the first stars form. And the second is magnetospheres and space environments of habitable planets. I'm going to talk about both of those science cases, but with reference to specific radio telescope designs that we've worked on over the last few years. The other reason it's taken so long is lack of access to the moon, because in 1972, with the end of the Apollo program, we really abandoned the moon, not just the US, but really the world. And only in the last decade have we begun returning to the moon with unmanned satellites and landers. China, Japan, India, the US all have major science instruments that have gone to the moon. And there really is a strong revitalization. This has been followed in the last couple of years by NASA's announcement of the new Artemis program, which is a return to the moon with humans. And the date currently set is 2024, although I think that's a bit ambitious. It'll probably be a little bit later than that. But nonetheless, there's a goal. And the equipment that's used for that will be the Orion crew capsule. And that's built right here in Colorado by Lockheed Martin. And along with a new heavy lift vehicle, the Space Launch System. The first test of this vehicle and Orion combination will be later this year, an uncrewed orbit of the moon, to be followed a few years later by a lunar landing with as NASA likes to talk about, the first woman and the next man to go to the moon. Now, equally exciting from the science perspective is that for the first time, the Science Mission Directorate at NASA has invested in lunar research on the surface through a program called the Commercial Lunar Payload Services. So what NASA is doing is they are buying services from about a dozen potential companies to fly landers to the moon and carry NASA-funded science payloads. Our radio telescopes are part of two of the early ones of these Eclipse landers that are going to the moon, that I'll talk a little bit about. So with access to the lunar far side, finally, after all of these years, it's going to open up really an unparalleled opportunity for us to do astrophysics and cosmology from the far side of the moon, taking advantage of the unique characteristics of radio quiet. The far side of the moon is in fact the only truly radio quiet environment in the inner solar system. It lacks a significant atmosphere, ionosphere. From our perspective, it is a dry, stable environment. So let's drill down on each of those just a little bit and contrast that with the Earth. So on the Earth, here's in the top picture is signal power versus frequency. This is a radio spectrum made with the LOFAR radio telescope in Europe. And you can see all of these low frequency interference spikes coming from a combination of private and defense related transmitters, just absolutely swamping the band. And so making it very difficult to observe. Going into space, you don't completely escape it either. This is a dynamic spectrum from NASA's Wind Waves satellite when it was in the vicinity of the moon, but not behind the moon. It was still facing the Earth. Frequency versus time. And you see all of these horizontal stripes. Once again, these are terrestrial transmitters breaking through the ionosphere and creating a background that is much, much higher than what is required to do low frequency cosmological observations. When you do go to the far side of the moon, as NASA did with the RAE-2 satellite in 1972, here's another dynamic spectrum. This is antenna temperature. Think of this as radio power per frequency bandwidth. So this is antenna temperature versus time. When the spacecraft was above the near side, you see all of this racket that Arthur C. Clarke was talking about. When you get above the far side, you're down to an ambient level where the galaxy, which is the brightest source in the radio sky, is easily visible at that point. The other problem on the Earth is the ionosphere. The ionosphere actually becomes opaque less than about 10, 15, 20 megahertz, depending upon where you are. Above that, though, even up to 100 megahertz, there are some severe ionospheric effects, as was articulated very nicely in this recently submitted paper to the Monthly Notices journal. It talks about the ionosphere both absorbing and refracting radio waves, and that without an ability to calibrate out the ionosphere at a level much, much greater than what we can do with any technology that's available now or probably in the future, then it completely swamps out any cosmological signal. Such a signal is shown below. I'm going to show a number of plots like this coming up in just a few minutes. This is brightness temperature versus frequency, and you can see a couple of broad absorption troughs, and the level is about 0.25 Kelvin. And the modeling done by this group from Cambridge indicated that would be completely swamped out. Again, that's not a problem on the moon because the ionosphere is at a much, much lower density and frequency. The third effect is ground-based artifacts, that the Earth has moisture, both the atmosphere and the ground, and very importantly, it changes with time, as does even things like vegetation. The radio telescope beams interact with all of that, and it interacts in such a way as without knowing these level of details, it's very difficult to remove those effects, especially when you need a precision observation to observe such a weak signal from the ground. We showed in this paper, led by my colleague Rich Bradley, that a number of ground artifacts and artifacts associated with the radio telescope can reproduce signals that may confuse between real cosmological signals and these systematic artifacts. So once again, going to the moon, you're free from all of those effects. And that's why, in part, NASA has selected this first payload called ROLSES. It's an acronym, and you see that acronym spelled out above here. It's led by my colleague, Bob McDowell at the NASA Goddard Space Flight Center. I'm a member of the team. And this set of radio antennas is going to fly on one of these commercial landers that I mentioned a moment ago, built by a company in Houston called Intuitive Machines. It's just going to carry a pair of dipole antennas, 3 meters above the surface. These are what are called stacer antennas. They're hollow tube antennas, very simple and lightweight. And a second pair, in this case, coming out perpendicular to the plane. This first experiment, which is going to be on the near side, so we're not taking full advantage of the radio quiet environment, is really a plasma experiment more than anything else. We're going to measure the ionosphere, if you will, in the vicinity of the lander. There's a lot of interest in the interaction. Mihai and Tobin study some of this, for example, interaction between the solar wind and charging the surface, creating a plasma in the vicinity. So using these radio telescopes and measuring the plasma frequency, we can constrain what that density is. But very importantly also, this is going to set the stage to allow us to understand the environment on the surface of the moon and our own protection against internally generated radio frequency interference, to validate that we can do clean radio observations from the surface of the moon. So that's due to launch in the fourth quarter of this year. So we're very excited to see that happen. That's going to be followed a few years later by a second one of these commercial payloads. This one is called LuSEE, Lunar Surface Electromagnetic Experiment. And this is led by Stuart Bale, colleague at UC Berkeley. Once again, I'm a co-I on this experiment. This one is going to fly to the far side. This will be the first US mission to the far side. It's going to go in the Schrodinger crater, which is inside the South Pole Aitken Basin, which is a large impact crater on the far side. So once again, a series of antennas to measure electric and magnetic fields, radio emission, measure the ionosphere, but also we have proposed to put a second antenna that I'll describe in just a moment, that combined with LuSEE will allow us to do the first cosmological observations from the surface of the moon. So these two are on their way. Both of these missions are scheduled by NASA. LuSEE and ROLSES are manifested on those landers. So let me talk about then this next experiment, which is to do cosmology, and this is the one I just mentioned, we'll add with LuSEE, potentially on the surface. This is called DAPPER. It stands for the Dark Ages Polarimeter Pathfinder. We were selected by NASA Astrophysics a couple years ago to do a mission concept study, and have subsequently been funded to continue the instrument development for this mission. We initially proposed it as an orbiter that you can see here in this picture that NRAO has put together for us. And it once again has these wire antennas, along with this box that you see on top. This is a patch antenna that I'll tell you more about. It has superb characteristics at somewhat higher frequencies. The team that's working on this, again, both now an orbiting mission and also looking at a lander, is shown here. This is led by our group at CU Boulder, and includes NASA Ames Research Center with help on project management, the National Radio Astronomy Observatory led by Rich Bradley, and then Stuart Bale and his colleagues at Berkeley. So what's the science that we're going to do? What's this cosmological science I've been talking about? So here is a cartoon picture looking at the evolution of the universe that I think will give us some idea of what we're looking at and where the gap is in our knowledge that we may be able to fill. The picture at the bottom here is literally the evolution of the universe from the Big Bang over on the left to today's universe about 13.8 billion years later on the right-hand side. Time is at the bottom. It's logarithmic in time. And there's a few redshifts that are located up over here, redshift 1000, 20, 8, and near zero of the current time. Now, a number of telescopes have been investigating both the very early stages here, where the cosmic microwave background occurs, such as the COBE and Planck satellites. And then a bit later, the Hubble Space Telescope and the upcoming James Webb Space Telescope, and some ground-based telescopes as well, investigating this epoch over here. But there's a huge gap in our knowledge of the universe. That gap begins at the end of the cosmic microwave background. This CMB appears at what's called the epoch of recombination. That's when the first atoms of neutral hydrogen form. The universe becomes transparent for the first time, and we're able to see the so-called baby picture of the early universe that these satellites had explored so magnificently. This is also the beginning of the Dark Ages. So the reason it's called the Dark Ages is because there's no stars or galaxies, there's no points-like objects, if you will, that are producing radiation. But there's still a lot going on. The universe at this point is filled with neutral hydrogen, and we'll come back to why that's important in just a moment. And it's also overdensities are collapsing down to produce what will become the first stars and galaxies. In fact, as you continue on, going then a little bit further out to redshifts, maybe about 30 or so, we really don't know, the first stars form. Models indicate those first stars are very massive, 100 times the mass of the sun, and they radiate prodigiously at ultraviolet. And those first stars also ionize the surrounding intergalactic medium. As more stars turn on over time, more and more of these ionized bubbles are blown. And finally, you have this last phase transition in the universe in which you go from what was an all neutral to an all ionized intergalactic medium as a result of those stars. So this makes for a good picture, a plausible picture, but we have no data to verify it in this very large region over here in the cosmic dark ages and cosmic dawn. Now, I mentioned before, we do have a potential way of investigating it, and is the neutral hydrogen has a hyperfine transition that when redshifted, so the observations that we see come in at very low radio frequencies, we have a tool to be able to probe this early epoch of the universe. Because neutral hydrogen is ubiquitous in the early universe, even a modest size single antenna or single set of antennas is capable of being able to detect the global signal. Now, of course, this area of cosmology has generated a lot of interest. I mean, you just look, for example, at the physics Nobel Prizes in cosmology. There's 1, 2, 3, 4 Nobel Prizes in roughly the last 20, 30 years that have been given out. 2 for CMB observations, 1 by our old friend and colleague Jim Peebles for the theory that he did in the 1960s on the CMB and basic cosmology. And then another one for the accelerating expansion of the universe that is thought to be due to so-called dark energy done with the Hubble Space Telescope at a later time. But once again, all of this work is at earlier times and later times than what we are proposing to probe with the lunar telescopes for the dark ages and the cosmic dawn. So let's talk a little bit now about this signal that we're going to use. So this is called the global 21 centimeter signal. Think of this as very similar to the COBE observations of the CMB, in which they magnificently measured with extraordinary precision the black body radiation coming from the early universe, as well as seeing the first perturbations in the sky background. So the signal, this 21 centimeter signal, comes from this hyperfine transition of the ground state of neutral hydrogen. It's called a spin flip transition. The cartoon picture you see here, in which the spin angular momentum of the nucleus and the electron are shown again in this cartoon. When this flips, one or the other flips, of the electron. This produces a photon at a frequency of 1.4 gigahertz, or a rest wavelength of 21 centimeters. As I said before, because the universe is expanding, this stretches out the wavelength by 1 plus z. And so at the redshifts we're interested in, this has shifted the frequency all the way down to, in some cases, a few tens of megahertz. On the right-hand side here, you see what we think the signal should look like. These are models of the signal. This is brightness temperature measured against the CMB versus frequency. And all of the models, well, let me just mention one other thing too that's different from the CMB, and that is because we're dealing with a spectral line, then that spectral line also, as we sweep through frequency, sweeps through redshift. So the CMB is one epoch of the universe. With the 21 centimeter global signal, we're able to explore the evolution of the intergalactic medium over a large range in redshift. So low frequencies correspond to early times, the dark ages, higher frequencies to the cosmic dawn that we're looking at. You see that in all of these models, there are basically two of these absorption troughs. Here's one, this dash one I call the standard model. This is the standard lambda CDM cosmology model. The CDM is cold dark matter, lambda is the cosmological constant, assuming a flat universe. In addition, for this part, we also assume through the modeling standard star formation, similar to stars we see in the local universe. And then there's also a trough in the dark ages, which is very simple physics. In the dark ages, there's no astrophysics. That is, as I mentioned before, there's no stars or galaxies. So there's only cosmology. And in this case, the reason there's a trough is because there's a difference in the cooling rate between the CMB and the baryons. And it produces then this trough with a very specific prediction of the amplitude of the trough and the frequency at which it should appear. The exciting thing about this is any deviation from this is going to indicate new physics, interesting physics, some deviation from either standard cosmology or some interesting characteristics of physics, such as dark matter, warm dark matter, cold dark matter. And that was suggested by this observation that you see actually in gray here. This says edges result. This is from a colleague of ours at Arizona State University, Judd Bowman, who using observations in Western Australia, claimed the detection of this signal, which is controversial. But if it were to be validated, would suggest that this signal is very different from what we expected with the standard model. And in fact, it does require new physics. One such new physics that has generated literally hundreds of paper in the physics and astrophysics literature is the possibility of added cooling to the baryons produced by Rutherford-like non-gravitational interaction between dark matter and baryons. That's quite unexpected and would be very exciting to help us understand dark matter if that were true. The color curves that you see here are some parametric cooling models that we put together, all consistent with edges. The nice thing about this is they break apart very nicely at the dark ages and would allow us to differentiate between different models of cooling, dark matter, early dark energy, other forms of physics that we could uniquely probe here. So that's one of the reasons we're excited to get to this dark ages. Let me also mention that when we get to the cosmic dawn trough, the reason this trough appears at all is because when the first stars turn on, the ultraviolet light couples with the hyperfine transition of neutral hydrogen through something called the Voigt-Hausen field effect that was predicted in the 1950s. and it drives this absorption trough. So where this turning point in frequency occurs actually is an indication, for the first time would be an indication of when those first stars turn on. And the shape of this also indicates the parameters of those first stars. The turnover at the bottom here, going back up, is thought to be due to when the first accreting black holes, probably the remnants of those first stars, they begin emitting X-rays, which then heats the intergalactic medium. So just a lot of really fascinating physics and astrophysics that's embedded in that signal. So I'm going to skip that plot so I can show this one. This is a numerical simulation that shows the evolution of neutral hydrogen when the stars turn on. So the black region is neutral hydrogen. The blue is then the vicinities of stars turning on, blowing those Lyman alpha bubbles. And you can see this cube turning and also evolving. Those of you who are Star Trek fans, I like to think about this as the Borg cube of cosmology. But you can see that over time, then, the universe makes this transition from what was an all neutral to an all ionized intergalactic medium. So with DAPPER, our goals are pretty straightforward. Our two objectives are to observe the dark ages and to observe this cosmic dawn trough, to validate or not in a clean environment where we're not affected by all of the systematics that are present on the ground. We're going to try to address this fundamental question: will the observed behavior of neutral hydrogen redefine the standard cosmological model and, potentially introduce some of this new physics? And I've only just touched upon some of the physics, and maybe we want to talk a little bit about that later. This is still a hard experiment. Even away from all of those effects on the Earth, we still have to look through a very bright galaxy foreground into the cosmological structures that we're looking at. So this is brightness, temperature. Once again, this is logarithmic this time versus frequency. And this shows in red the expected 21 centimeter global signal. And then the brightness, though, of the foreground, of the galaxy foreground, which you can see is 4 to as high as 6 orders of magnitude greater than the 21 centimeter signal that we're looking for. And so this is significant, but it's really not much different than what the CMB is facing, particularly CMB polarization observations that are looking for these so-called B modes, indicators of inflation. The way we deal with this is actually in a somewhat similar fashion to CMB, and that is we take advantage of the fact that the spectral shapes for the galaxy, this is just synchrotron radiation, which is essentially a power law. That is different than the 21 centimeter. There is spatial structure in our galaxy. Even with the huge beam that we have, we will sweep through that spatial structure. There is no such structure in the 21 centimeter signal at these scales that we're looking at. It's homogeneous and isotropic. And then also the foreground is polarized, whereas the 21 centimeter is not, and we can take advantage of that as well. So those are 3 things that go into this. Now, in terms of the technology, as I alluded to in a slide back a little bit ago, we are using 2 antennas so we can span this very wide frequency range going from 10 to 110 megahertz. The low band is very simple wire antennas that have flown hundreds of times in space. And then this high band antenna, which is also versions of this at higher frequency, have flown also many, many times in space. And we're doing an engineering scale up to the size and down in frequency. In fact, here is a laboratory model done once again by my colleague Rich Bradley at NRAO, a 1/15 scale model that he's recently built. It's a high dielectric material, has wonderful beam properties that you see here in this electromagnetic model of the telescope beam. it varies smoothly with frequency. And it's divided into 4 quadrants so we can measure the polarization as we do with cross dipole antenna.
Jack, we do have a couple of questions in the chat.
Oh, okay. Yeah, let me slow down here a little bit and try to feel those questions. Sorry,
yeah, I think
that's blowing through those.
Relevant time to ask both of them. One's from YouTube. These folks can't ask it orally, but I guess there's a way of forwarding their chat request. This is from Steve Pollock, who asked, how do you receive the signals back from the far side?
Yeah, good question. So in the case of the orbiting antenna, we take data when we're above the far side and then dump the data back to Earth when we're at the near side. When we're on the surface, NASA has committed with the Schrodinger mission to put a transmission satellite that will relay the data from the far side back to Earth.
Mm-hmm. Eric Cornell also has some questions. Eric, would you just like to ask your questions yourself?
Sure. My questions are, as you orbit the moon, will the galactic signal be modulated? And can you use that to help calibrate it out?
Yes, absolutely, Eric. That's a great question, and that is part of our strategy. That is what I meant by there being some structure in the foreground. So both the polarization and the Stokes eye change as, for example, if we're orbiting or if we're on the surface and the sky is drifting over, we take advantage of that to remove the signal. And that's a key part of our data analysis pipeline.
I guess the other thing I wanted to ask along those lines is, I know you have to be on the side of the moon away from the Earth. Do you also have to be on the side of the moon away from the sun? Are those sort of wedges where you can take data, or is the sun not so important to you?
Yeah, that's another good question, because the sun is much less bright at optical wavelengths. In fact, it's 100,000 times dimmer at 40 megahertz than is the galaxy. And so it's really a sort of weak point source that is not quite in the noise, but still is there. And that's the quiet sun. Now, when it bursts to produce a coronal mass ejection, then it will swamp out the data. Fortunately, those radio bursts only last a few hours at most, so it's easy to recognize and to just delete the data.
Thank you.
All right, let me just mention that the receiver that we're using is a standard, at least in radio astronomy, a 4-channel correlation receiver. So what we do is we take the 4 monopoles, for example, and we cross-correlate those. So that's very good at removing just noise, shot noise coming from the solar wind. We also have a frequency tone that we will use to measure the changes in the gain of the instrument. We think we can do that to a few parts in 10 to the 6th, which is going to get us the kind of dynamic range that we need. And also we're going to maintain the temperature to plus or minus about 1 C during the mission. The receiver version of this has actually been built. You see here, this is built by NRAO, a higher frequency version of this. And this is going on the Green Bank 100-meter telescope later this fall. And this is a nice scale up of the receiver that will be used for DAPPER, which is also going in the field. Some additional heritage here. My now former student, Bang Nan, who is now a Jansky postdoctoral fellow at NRAO, built this polarization antenna for his PhD dissertation, in which he was able to demonstrate for the first time this dynamic polarimetry from the sky, that is to measure that low frequency polarization and to calibrate it in such a way that we'll be able to use it for our DAPPER observations. Finally, the data analysis pipeline, and this is what part of what Eric was mentioning in here. Our observation strategy and I should say a lot of our work here at CU is focused on the data analysis pipeline, because our work is mostly devoted to that. Our observation strategy is to look at the time dependence of the total intensity and polarization, and using that as the sky changes to differentiate those changes in the foreground versus the 21 centimeter global signal. And what we do is we use a Bayesian inference approach using pattern recognition, and then a series of training sets or modeling sets of the instrument, of the foreground, and also of the potential signals, and use singular value decomposition to make those fits. And in this case, where we're dealing with such a high dynamic range observations, we can't just do a simple subtraction of the foreground from the signal. That in fact, we have to do these kind of simultaneous fit using this approach. So a cartoon picture of that extraction, I'll show you some real ones in just a moment. The last step of our pipeline is to then use a Markov chain Monte Carlo sampling to do physical model extractions. For example, in the case of the added cooling models, this would be the time when the added cooling starts, and also what the cooling rate is, that again would give us a handle on what physics is generating that cooling. This has all been developed in a series of papers that have been published. In fact, we have about a half a dozen published in the last 2 years in the Astrophysical Journal. So last part of this, let me just mention, I said we've been initially studying this in orbit. We've also more recently looked at putting our DAPPER high frequency antenna onto the lander that LuSEE is going to be on. And this is a cartoon picture of the LuSEE dipoles. And what we've done is some modeling of that. We've done some electromagnetic modeling of the interaction of the antenna with the lander and the dielectric material that makes up the regolith. We've looked at the beam structures. Once again, they're nice, they're smooth, they vary nicely in frequency, which is very important for us, again, to be able to differentiate between the foreground and the signal. So on the left-hand side, this is what we proposed to NASA just a couple of weeks ago of what we think we can do from the surface of the moon by adding the DAPPER antenna to LuSEE. This is brightness temperature, once again, measured against CMB versus frequency. The green shows the 68 and 95% confidence intervals. The dashed is the standard lambda CDM cosmological model, and the green is an added cooling model. This shows the degree of precision that we can do in these first observations, and also to be able to separate out added cooling models from the standard models. These other pictures just indicate that doing LuSEE observations alone are insufficient to really be able to constrain the dark ages. DAPPER alone could do a reasonable job of the cosmic dawn, but not as good as when we combine these together. So this is what was proposed. We're hoping to get a positive reaction from NASA to add that additional antenna. So let me move on to the last part of the talk, which is the next telescope that we want to put onto the far side of the moon. And this is a radio array. It's called FARSIDE. It's an acronym that you see spelled out over here at the top. It's for dark ages and exoplanets. My deputy principal investigator is Greg Hallinan at Caltech, and JPL was our team partner. They did an absolutely magnificent job in the engineering. We were selected to do what NASA has called a probe class study. This is a new set of NASA satellites, probes that go up to $1 billion. They're still PI led. In our engineering study, which we presented to the decadal survey, we use one of NASA's new human landers that are capable of carrying several metric tons or more to the lunar surface. And here we actually worked with Blue Origin, Jeff Bezos' company in Seattle, on this. And we deploy our antennas with a series of single axle rovers that you see over here that have been pioneered by JPL. And these tethers contain both the antennas as well as comms and power. We lay out this array of 256 dipole antennas in a spiral-like pattern over a diameter of about 10 kilometers altogether. We can get this all done in one lander payload, and be able to operate this with currently available technologies. So here's some of the science. In addition to the cosmology, we have the opportunity with this array to study space weather and exoplanet magnetospheres. Here's one of these coronal mass ejections I was mentioning a little bit ago, which on the left is a Mars-like planet, on the right an Earth-like planet. The difference, of course, being the magnetic field. We know from observations that have been done of Mars by satellites here at CU that the atmosphere of Mars was stripped after its magnetic field turned off, and it went from what was a wet planet to a bone-dry desert planet today. The Earth went into a very different evolution because we think of the protection of the magnetic field. But that magnetic field also lights up when one of these coronal mass ejections come by. It produces sort of a classic, as you see here, an aurora, but also it also produces auroral radio radiation, which we could potentially detect for exoplanets. So with this array, we actually have an opportunity to measure, using low frequency radio observations, this space weather, coronal mass ejections, and planetary magnetic fields. Let me just show you a little bit more about this. Most of the exoplanets in our vicinity are M-dwarf stars, and they flare much more so, as you saw here. You saw a comparison of a large solar flare and an M-dwarf flare. And these things, therefore, may be very harmful for any potential life that might be there. So we would like to be able to study these systems. Here's a highly stylized cartoon picture of an M-dwarf star and a number of these coronal mass ejections, which are shocks. And these shocks reaccelerate electrons, amplify magnetic fields, and produce what are called type 2 radio bursts. Here, this shock also energizes particles in the magnetic field and causes the magnetic field to light up by orders of magnitude, producing an auroral kilometric radiation. This shows you what this looks like for the case of the sun. On the left-hand side, this is a white light video. On the right side is the radio emission, frequency versus time. And you can see the radio emission is almost all below 10 megahertz, all below the ionospheric cutoff. So in order to do that space weather plus look for these magnetic field radio emission, we've got to go to telescopes that are on the surface of the moon, because almost all of this radio emission, with the exception of Jupiter, is below the ionospheric cutoff. The emission from the magnetosphere is electron cyclotron maser emission, where the frequency is directly proportional to the magnetic field. Only Jupiter has a magnetic field that's strong enough to show up above 10 megahertz. Everything else, including the Earth, are below. So clearly we need to have a low frequency radio telescope, not only with lots of sensitivity, but also an ability to go below 10 megahertz down to a few hundred kilohertz. So the FARSIDE mission architecture is shown here. Our array that we're proposing will operate between 100 kilohertz up to 40 megahertz. And this somewhat busy plot, though, shows most everything that we're going to do on the lander, which also serves as our base station. We have our computers, our correlator, the battery power, and that will be recharged during the lunar day, and then possibly relaying the comms back to the gateway, which is a NASA orbiting platform. And then these rovers will string out these tethers that will contain antennas that are 100 meters tip to tip within the tether, as well as comms and data relay and power that will go back as well. So we work with, as I said, we work with Blue Origin on how we could pack these initial Axel rovers onto their lander. We've done it here. They're spring loaded so that once the lander is on the surface, they just pop out, and then we lower them to the surface and they go on and do their thing. The size of the rover is considerable, you see here. Here's a rover length in units of Elon Musk that you have here. So just to give you some ideas, so it's 2.3 meters in diameter. So these are big things. The spool assembly here contains not only the tether, but we've also flattened all of the electronics so that the receiver electronics fit onto this spool assembly. And we're also dealing with low temperature electronics that are capable of surviving the night that that JPL and others have done. Let me show you an example of one of these Axel rovers, and I'll just advance this a little bit here, give you some idea of what this looks like. So this is an experiment we did in the so-called Mars yard. This is distributing a polyamide tether that would also be an antenna in this particular case. So this rover is already at advanced TRL level. This can be either teleoperated by astronauts, say at the gateway, or from Earth, either one, to be able to do this. So let's see, let me just advance here. So we've done some synthetic observations, that is, we've done some modeling of what this radio array would see. For example, a solar type 2 radio burst in our solar system. We've actually put the array down on the lunar surface in a particular location with a variation of elevation. This produces what radio astronomers call a UV coverage. So this is actually the projected baselines. And the idea being that for an instantaneous UV coverage, you like this to be filled as much as possible because it produces a very nice symmetrical beam. Here is a model, MHD model that we did of a shock wave that is part of the coronal mass ejection. We then synthesize the radio emission that would be produced, observe it through the array, and this is the synthetic map that we see of that. We do a good job of resolving it in both directions. This kind of observation has never been done before. We've never been able to map the radio emission from these telescopes. So the operations of this array are well in hand because we've built these on the ground. This is my colleague Greg Hallinen's long wavelength array at Owens Valley in Caltech. This is hundreds of dipoles. So the instrumentation, the data analysis, the operational techniques are all well in hand. Much of what we want to do with this array is we'll be able to do maps of the entire sky in 1 minute intervals over a frequency range from 100 kilohertz to 40 megahertz in 1,400 channels. The idea being that we would identify regions that are bursting on the sky for nearby nearby exoplanet systems. We can monitor about 4,000 of those nearby systems. The bursting come from coronal mass ejections and also from the magnetospheres that will be lit up, and they'll have different polarization properties than the solar weather. We project that we will be able to see several dozen of these. This is flux density versus distance of nearby systems. The difference in colors represent different models of how the magnetospheres will be energized, but this initial array will be capable of detecting those. So being able to see magnetic fields associated with exoplanets, this is the only way we could do this. And these magnetic fields may be an essential element into whether or not these exoplanets are potentially habitable. So it's the second major science case. So just to summarize, then we've got now finally, after many years, a real return to the moon by NASA, ESA, and other space agencies. The CLPS program is going to put our first radio telescopes on the moon, and hopefully followed in short order by our cosmology DAPPER telescope and our FARSIDE array. One last thing that we're doing, I'll just show, is we're also doing a new planetarium show at the Fisk Planetarium called Forward to the Moon as part of this outreach to the public and our students of what we're planning to do from the moon, all for educating young folks like what you see over here. This is my grandson, Lucas. You got to show pictures of your grandchildren, right? So he's 1 year old, just turned 1 year old, and he's clearly very intensely studying his astronomy book, and he's figuring out how is he going to help grandpa by putting those telescopes on the moon. So Mike, I will stop there. Happy to take some questions at this point.
Thank you very much, Jack. We do have a question from chat from Dmitry Uzdensky, and we have a hand from Mike Schultz. So Dmitry, if you're still here, would you like to ask your question?
Yes, thank you very much, Michael. And thank you, Jack, for the very interesting talk, very exciting scientifically. My question is that you talked about interesting applications to cosmology and to extrasolar planets, which are both very interesting, but are there any potentially interesting applications to the usual radio objects, such as radio pulsars and AGNs, radio galaxies, things like that?
Yeah, sorry, I didn't have a chance to cover all of those, but particularly with the radio array, it is really an observatory on the moon. So we've defined 6 or 8 science cases of what we want to do. Certainly pulsars at low radio frequencies, maybe even fast radio bursts. They've been seen recently down to about 150 megahertz. Could be very interesting. But also we plan to use the array to do radio sounding of the subsurface, which is an interesting area. So we use
the surface of the moon.
From, for example, we can do passive sounding or active radar sounding, and spread over an area of 10 plus kilometers, we could understand the subsurface structure. So you're absolutely right. This is really as an observatory to do a number of observations. Other things we can do is within our solar system is we can measure lightning from Uranus and Neptune, which was seen by Voyager, but is not possible to see with any other telescopes from the Earth. So things like that will be in the offing.
So in addition to these specific areas, you envision this as a general purpose observatory who will study whatever it finds, right?
We do.
Okay.
Absolutely. Great. We do.
Thank you.
Mike?
Yes, hi, Jack. A lot of your work you talked about was 80 megahertz and below, but of course the universe is still reionizing down to redshift 765. So I wonder if you have plans for going up to 150 or 200 megahertz to study that later stage of reionization?
Yeah, that's a good question as well. And there we're going to leave it for the ground-based arrays, like the Hera array or the SKA. Those are underway as well. I think certainly above 100 megahertz or so, those arrays hopefully will be capable of doing measurements, for example, of the power spectrum, the angular power spectrum, which is going to be very interesting in the epoch of reionization, the late stages of cosmic dawn. So we look forward to that. But of course, we'll find out, because it is difficult to observe from the ground. There are some fundamental problems. The ionosphere, even at those high frequencies, they really crush down the parameter space that one can really see, the so-called K space that one can really see these structures in. So that's yet to be determined. If we can't do it, well, on the Earth, then we go to the moon.
Maybe we could take one last question from Scott Diddams. Scott's still here.
Yeah, hey, thanks for the nice talk, and that was really interesting and well presented. I had a very technical question. What is the expected power received of this 21 centimeter line in your DAPPER experiment?
Yeah, so we work in these units of brightness temperature or antenna temperature, but we can kind of put it into perspective. So when we look at the Earth from the near side, the brightness temperature of the Earth due to radio frequency interference is about 750,000 Kelvin. The signals we're looking for are in the tens to hundreds of millikelvin. So very similar to the difference between what the CMB polarization is going after versus the foreground. In this case, with CMB, they are issues of dust in our galaxy. In our case, it's synchrotron radiation. So these are very, very faint signals. But still, the nice thing about this being a global signal, that's why I mentioned before, even with a single dipole, in a good environment, there is still enough sensitivity over a period of less than 1,000 hours to do a clear detection of the signal.
All right, great. Thank you.
So Jack, thank you so much again for this outstanding colloquium today. I really enjoyed it. I think.
Thank you, Mike. I'm sorry I went on a little bit longer than I had intended, but I think I have an opportunity to meet with some of the graduate students later today as well to continue this discussion.
So we'll thank you again with our applauding yellow hands. A few real hands.